Hi, my name is Kishen Shanmuga Raju and my matrix number is 241110930. And today I'm going to explain about Reynolds transport theorem. Reynolds transport theorem, or as in short, RTT, bridges the system approach and the control volume approach. The system approach is tracking fluid particles, and the control volume approach is examining a fixed region in space through fluid flow. Yeah, the diagram shows two methods of analyzing the spraying deodorant from a spray can. As we learned, the fluid as it moves and deforms is called system approach because there are no mass crosses the boundaries and the total mass of the system remains fixed. In another case, a fixed interior volume of the can is called control volume approach because the masses crosses the boundaries. The relationship between the time rate of change of an extensive property for a system and for a control volume is expressed by RTT. RTT is divided into two components, which is unsteady accumulation on how property B of the system accumulates within the control volume and flux across the boundaries, which explains how property B flow across the boundary, the control surface. In this diagram, it shows a control volume with fluid flowing through it. The arrows indicate velocity vector representing fluid flow through the control surface and exiting the system. In this case, we must use equation total derivative of B's property system equals to total derivative of property of control volume minus intensive property plus extensive property. This equation applies at any instant in time where it is assumed that the system and the control volume occupies the same space at particular instant in time. In this slide, it shows how the formula is formed. The diagram shows a steady state system. The mass entering the control volume must equal to the mass exiting or leaving the system. This ensures that the property B is conserved and there is no accumulation within the control system. So, in this case, net of property B is equals to extensive minus intensive property, which is equals to total derivative of control surface density of fluid times property times relative velocity times unit normal vector times area element on the control surface. So, outflow and inflow of mass across the differential area of a control surface RTD fixed CV. Total derivative system is equals to total derivative of control volume plus control surface. In alternate RTT, it's also shown that total derivative of control volume plus the property net, as you can see from here. Next, we should look onto the relative velocity, which is relative velocity equals to absolute velocity minus control surface of velocity. In non-fixed CV control volume, RTT is the formula for RTT is derivative of property B. Total derivative of property B is equals to total derivative of control volume plus total derivative of control surface. The relative velocity crossing a control surface is found by vector addition of the absolute velocity of the fluid and the negative of the local velocity of the control surface. So this is the diagram for absolute reference frame and relative reference frame. Next, we see how is the formula for property property B in terms of inlet and outlet. So the formula is total derivative of control volume plus outlet minus inlet. An example control volume in which there is one well-defined inlet and two well-defined outlet. In such cases, the control surface integral in the RTT can be more conveniently written in the term of the average value of fluid properties crossing in each outlet. So, that's it for today.